Hello everyone. Today we will start our peripheral section. In this peripheral and interfacing devices, we will firstly go through the 8088 Intel memory and interfacing. First of all, we already know what is microprocessor and what is microprocessor system. Now, in this session, we will start with the memory structures and interfacing. Structure is an architecture and the interfacing is to intercommunication. So moving on. Topics of reading. First of all, we will know about memory types. Then interfacing 8-bit memory, 16-bit and interfacing 32 or 16-bit memory I/O. I/O means input and output. 8-bit is for 8088 and 16-bit is for 8086 microprocessor. Now moving to the next, the memory types. What is read-only memory or ROM? We already know what is read-only memory or ROM is. This is a memory which is used to store the memory and some other elements permanently. When we need to access this, we can easily edit, access or read from the ROM, which is only read-only memory and which is non-volatile. That means if you turn off the power of this computer, this will not remove the memory or the elements. There are some types. First one is ROM, which is read-only memory. In this section, programmed during fabrication at factory, and now control program is dedicated system is stored in the ROM. We already know about ROM, and this is the type of a ROM which is called the PROM or programmable read-only memory. Now this PROM is programmed by burning tin or silicon oxide fuses, and once programmed it cannot be erased. So this is a non-erasable programmable read-only memory which is known as PROM. Then we have the eprom, which is erasable programming read-only memory. In this eprom, the ROM can be erasable, but in programmable read-only memory the ROM was not. Memory can be erased by exposure to UV light. That means this EPROM uses UV light to burn the ROM and can be programmed by users, but it is usually removed to erase. Here are some examples given below. Now, EEPROM, which is electrically erasable programmable read-only memory. That means this ROM is erasable, that is programmable, but this one is also electrically, because the EPROM uses UV light, but in this section it will use the electrical or electricity section, also called a flash memory, which is by the Intel, or EARM, electrically alterable ROM. This can be erased and reprogrammed, which is the basic and main features of EEPROM, and by the system. We generally use the EEPROM in our desktop or laptops nowadays. Now the RAM, which is known as the random access memory. There are some types. First one is the SRAM, which is static random access memory. Retains data for as long as the power applied. That means that random access memory will only hold the memory or the location when the power is supplied to your devices. If the electricity gone or the PC is shut down, then the RAM section will be empty. This is first expensive big, and higher gate count is 4 or 6. It needs a flip-flop. We already know what is flip and flop. In this, if you don't know, you can simply see this diagram. Here, one section is called the flip and another is called the flop. If you input here 0, it will get the 1, and if you input as a 1, this will bring you a 0. So this work as a flip and this work as a flop. This is the major idea of flip-flop. That's how it stores the data in RAM, which is known as static RAM or random access memory. Now moving to the next, random access memory, which another one is the dynamic random access memory. In the static RAM, we don't need to refresh, but in dynamic RAM, we need to refresh in again and again because it retains data for only 2 to 4 milliseconds. Then it must be refreshed. It is slower but cheaper and can also be large to 2 GB DIMM and high density with 1 transistor pulse capacitor. So in this section in dynamic RAM, we can also notice that here we are using the capacitor, and in the static RAM we have already used the flip-flop section, and dynamic RAM can be refreshed, but the SRAM doesn't need to refresh. So this is the diagram of dynamic RAM. Now here are the memory types. Here is a DRAM device. Here G is for ground, VSS is for source, and here address pins are multiplied. Then A0 to A7 loaded the first with RAS, which is row address selection, and A8 to A15 is loaded the second with CAS, which is column address select. Now CA also serves as a chip selection in the DRAM devices. You can have a snap of this one. Now we are in the memory type section. This is a very important diagram for your exam point of view. I will give the link of the slide in the description below. Now moving to the forward. Here are some types of DRAM. DRAM have EDO, which is for standard data output DRAM. Here we need to bit selection by RAS, which divides on the row section are latched. Faster for sequential address and no wait state for sequential accesses. Now SDRAM, which is synchronous synchronous dynamic RAM, which is faster, access time is 10 nanoseconds to 8 nanoseconds. It is internal state machine tied to system clock controlling operations, used for burst read for 16-bit numbers. What is DDR? We are already familiar with it because we are using laptops and PCs where we have the DDR RAMs, which are double data rate. In DDR, we have to generate a clock pulse. In the clock pulse, we can have data in the top of the clock and also below of the clock. I will draw a diagram for this DDR in later videos. And now, what is RDRAM, which is for rambus DRAM. Now moving to the next. Here is the diagram of a generic memory. Here is the right function. The bar means it will work only on when the voltage is low or the input is low. Selection and read are also same. The most important line is that n addresses lines can be addressed to n memory location. Here the size is 1k, that means 2 to the power 10, and 2 to the power 10 generates 1024, which is the 1 kilobyte. Here we are using line tens, means 2 to the power 10 means here a line is 10, and from this range we can have 0 to 3ff. You can easily count this value by turning it into a hexadecimal number. Now 2k means 2048, which is 2 to the power 11. So here the line number is 11, and the value can be counted easily by scientific calculators. Now this is for 4k, which is 2 to the power 12, and now 1 million, which is for 2 to the power 20. So here the line number is 20. Now moving to the next step of success. Here are some architectural questions. Those architectural questions will be asked in your exam questions. We will discuss it with examples further. Moving on to the next. Design an interface for a 8088 microprocessor to connect a single line, which is 2716. In 2716 we can generate this by 2k into 8, which is eprom, such as that memory starts from at ff800h. The 8088 has 20 address lines. Highest address line is 20 and 8 data lines. So the 2716 has one chip selection pin and one output enable pin. The logic gates are established are NAND, NOR and NOT may be used in this section. 2716 are generated by 2k into 8 eprom. Now the answer of those questions. First, how many chips are required? Here chips are required 1. How many address line for each chips? Here we have 2 to the power 10. That means 2716 has to be generated. 2k equals to 21. This 21 means 2 to the power 1, and this 210 means 2 to the power 10. So the total location is 2 to the power 11. So here are 11 address lines to generate 2716 chip. How will chips be organized into a bank, and which part of those address buses are used? Only 8-bit data bus and only one bank. What is the bank? We will discuss further. Now moving on to the next question. Here the determine address range. Here we started from FF800, which was declared, and now what is the size? In this section the size is 800, which is around 2k. We need to generate the sequence of 800h. The lowest or start address is FF800 and high address is FFFFF, which we can generate by FF800 plus 800h, which is the size, and then minus 1. Now here we can have the diagram, which is we can see that the started address was FF800. Here this one is for a F, this one is for another F, and this is for the 8 number position, and then all other sections are 0. We generated FF800. Then the final state FFFF which is generated by this one is for 1F, 2F, 3F, 4F, and the fifth one. So this is the final destination FFFF. Now some questions looks like this. In the decode section we have 11 to 19 all are 1. In this section we have only one only when A19 through 18 all are ones from the starting position to the ending position. Here is the 8-bit interfacing example. What are the generate of banks and write the significance of the requires. Is it required here any banks? No. Here is the diagram for this section. This we have already discussed. You can have a glance of this diagram. Here DDD is to decode to select memory address and MMM is to memory device depending. Here are the logical components where we use the NAND NOR or NOT. Now the address decoding section. We will discuss it into the next slide.